Hello, and welcome to this presentation on the Newton-Raphson method. This is a numerical method used to iteratively solve certain types of equation. An overview to the solution of equations. Exercise 1. We're asked to solve the following three equations. Part 1. We've got a half of x minus 3 is equal to 1. This is a simple equation which we solve by transposing for x. Part 2, we're asked to solve the equation t squared minus 3t plus 2 is equal to 0. This is a quadratic equation in terms of t, which we can solve using factorization or the quadratic formula. In part 3, sine theta is equal to a half. This is a trigonometric equation we need to solve for angle theta. The answers to these problems are shown on the right hand side in the brackets. I would encourage you to stop the presentation and attempt the solution of these three equations. Worked solutions are shown on the following slides. Exercise 1 solution, this is part 1. We've got the equation half multiplied by x minus 3 is equal to 1. This is called a simple equation. To solve this we simply rearrange for x. So given a half multiplied by x minus 3 is equal to 1, we add 3 to both sides of the equation, get a half multiplied by x is equal to 4, and then we multiply both sides by 2 to get 1x on the left hand side, or simply x, is equal to 4 times 2 is 8. We can check the answer for x by substituting this back into the original equation and seeing if the equation balances. Exercise 1 continued, part 2. We're given the equation t squared minus 3t plus 2 is equal to 0. This is a quadratic equation of the generic form ax squared plus bx plus c is equal to 0, where x in this case is t. The constants a, positive 1, b, negative 3, and c, positive 2. The quadratic formula is stated as x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. What we're going to do now is substitute the values of a, b and c into the quadratic formula shown above, but we're solving for, in this case, t, as our quadratic equation is in terms of t. So the equation states it's negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So that's negative a negative 3 plus or minus the square root of negative 3 squared minus 4 multiplied by 1 multiplied by 2, all divided by 2 times 1. I'll let you follow the numerical workings here, and you should eventually find that the value of t is 2 or 1. I've solved this using the quadratic formula. You could solve this using the factorization method. Exercise 1 continued, part 3. We're given the equation sine theta is equal to a half. We've got to solve for theta, so we take the inverse sine of both sides of the equation. That leaves us with theta is equal to sine to the minus 1 of the 0.5, the half. And that gives us two values between 0 and 360 degrees of 30 degrees or 150 degrees. And we can see that on the graph. For the sine ratio of 0.5, we draw a horizontal line across to the sine curve. It hits here at 30 degrees, and if we continue that line across, it hits the curve here at 150 degrees. So between 0 and 360 degrees we have two solutions, 30 degrees and 150 degrees. Continuing here with our overview of the solution of equations, it can be noted that the previous equations are all solved directly by rearranging or using the appropriate formula. Such equations are termed explicit equations. However, the following equations cannot be rearranged and solved directly. For example, theta equals tan theta, negative 21.9 is equal to the natural log of 1 minus 5 divided by t in brackets, multiplied by the natural log in brackets of 1 minus 10t. That cannot be solved directly by rearranging or a formula. And also this equation here, 1 plus e to the negative 7.3 divided by t minus 2 multiplied by e to the negative minus 3 divided by t is equal to 0. Again, we cannot solve that directly by rearranging. So these are now termed implicit equations and must be solved using numerical methods. The Newton-Raphson method. The Newton-Raphson method is a numerical technique that can be used to solve implicit equations, as stated previously. If xi is the approximate value of the real root of the equation function of x is equal to 0, then a closer approximation of the root xi plus 1 can be given by the formula here. Xi plus 1 is equal to the xi, the initial approximation of the root, minus the function of xi divided by the function dash of xi, and that's the first derivative of xi in functional notation. Newton-Raphson method continued. The advantages of the Newton-Raphson formula over other methods of successive approximation techniques, such as, for example, the bisection method reviewed in a previous presentation, is that it can be used for any type of mathematical equation. For example, ones containing trigonometric, logarithmic, exponential, hyperbolic, and algebraic equations. Also, it's relatively easy to apply. Imagine the implicit equation of the form function of x is equal to 0 is to be solved. This is illustrated in figure 1. This is a plot of the equation function of x that we have to solve, and the root we're trying to solve for is actually shown here. If we start with an approximation x0 shown here, the tangent to the curve, y is function of x, our yellow curve, is drawn and cuts the x-axis at a location of x1, which is the next approximation. So in other words, here's our point on our curve, the function of x0. If we draw a tangent through this point to our curve, we will cut the x-axis at x1, which is our next iteration. The tangent to the curve at x1, the function of x1, is now drawn that cuts the x-axis at x2. So what we now do is consider this point, the function of x1, and we draw a tangent through this point to the curve, and it cuts the x-axis now at x2. This process is repeated until xn plus 1 minus xn is less than the required accuracy for the problem we're solving. To devise a formula for this method, let's consider figure 2 on the next slide. Newton-Raphson method continued. Here is figure 2. Assuming that the xn has been used to produce the value xn plus 1, the gradient at tangent CB, shown in figure 2, can be defined as, so gradient CB is equal to BA divided by CA. In other words, in our figure 2, if we divide BA, this dimension here, the vertical dimension, by CA, we get the gradient at point B. The first differential of y, the function of x, is written as function dash of xn. That's equal to BA divided by CA. So the gradient at CB can be written as function dash xn. That's called functional notation. However, the length BA in our diagram is actually the function of xn. In other words, the y value from our equation. So it can be seen by rearranging the lengths of CA can be written as BA divided by the gradient CB from this line here. And using notation from the line above, we can write BA as the function of xn, and we can write the gradient CB as the function dash xn. Further noting that length OC is OA minus CA. On figure 2, that is the distance OA along here minus the distance from C to A, shown here. Thus the xn plus 1, shown in figure 2, can be written as xn minus the function of xn divided by the function dash xn. And this is called the Newton-Raphson formula. Application of the formula. To use the Newton-Raphson equation, an initial estimate of the root location must be made. This is a numerical method, so we must have some initial indication of where the root lies. This can be achieved in several ways. We could insert values of x into the equation and look for where a change of sign occurs. We can use a rough sketch of the functions involved to try and indicate where the roots occur. Or we may be able to find the initial estimate from the physics of the problem, for example, the geometry. We need to be careful though, because if the initial choice of the root is poor, the Newton-Raphson technique may not converge. As the iterations unfold, we bounce around the root position and never home in on the root position. So we need to be careful that the estimate we have is reasonably close to the root to begin with. As the Newton-Raphson formula requires differentiation, within this work we will need some reference information related to standard derivatives, and I've included this in a table for convenience. In this particular presentation we will only be solving equations of the form ax to the n, so only differentiating the ax to the n format for the derivative shown here. However, the Newton-Raphson technique will work for sine functions, for cos functions, for exponential functions, etc. etc. Example 1 is an illustration of how to use the Newton-Raphson technique to solve for a root of a cubic equation. So we're given a cubic equation, x cubed divided by 3 plus x squared divided by 2 plus x is equal to 2. We're asked to solve this for a root to 3 decimal places. So initially we have to try and estimate the vicinity of the root. There are several ways of doing this. We could plot a curve and look where the curve crosses the x-axis, or we could use a trial and error method, which I'm going to use here. So initially then, to try and find the approximate location of a root, we're going to use the equation above in example 1 and write it in functional notation. So a function of x is equal to x to the 3 divided by 3 plus x to the 2 divided by 2 plus x minus 2 is equal to 0. Essentially what I've done there is take 2 from both sides of the equation, given example 1, to equate it to 0. What I'm going to do now is guess values of x and see if the remainder changes its sign. If the remainder changes its sign for values of x, I know I have a root between those values. So for example, let's let x is equal to 0 for our first trial. All we do now is put the value of 0 into our function of x equation and evaluate the remainder. So the function of 0 in this case will be 0 cubed divided by 3 following the above equation, plus then 0 squared divided by 2 plus 0 for the x, take away 2. So the remainder is negative 2, and it's a sign we're interested in particularly. For my next trial, I'm going to use x is equal to 1, so the function of x here is function on 1, so that's equal to 1 cubed divided by 3 plus 1 squared divided by 2 plus the 1 minus 2. Evaluating, I get another negative remainder. Now I'll try x is equal to 2. Function of x on now 2, so replace the x with a 2, so it's 2 cubed upon 3 plus 2 squared upon 2 plus 2 minus 2. Evaluating, and I'll get positive 4.6 recurring. So we've got a change of sign. So now we know that a root exists between x is equal to 1 and x is equal to 2. But note that the value of x seems to be closer to the value of 1 than 2 on the x-axis. So using the Newton-Raphson formula on the previous slide, we know that the next value of x, the next guess if you like, is based on our initial value of x minus the function of x divided by the function dash x. And that function dash x is a differential of the function of x. So what we need to do first of all, before we start our iterative process, is to differentiate the function of x. So f dash x, using function notation, is dy by dx in conventional Leibniz notation. In this case, that will be 3x squared upon 3. In other words, I'm differentiating the x cubed upon 3 using the ax to the n form from our standard derivative table shown here for convenience. And when I differentiate ax to the n with respect to x, I get the format of a multiplied by n multiplied x to the power of n minus 1. So my x cubed upon 3 becomes 3x squared upon 3. My x squared upon 2, following the pattern table 1, becomes plus 2x upon 2. My value of x in the function of x equation differentiates to 1x to the 0 if you follow the pattern through, and that all simplifies now to a function dash x equals to x squared plus x plus 1. If you're unsure or want to recap about the differentiation process, I would encourage you to revisit a previous presentation on differentiation standard forms. Example 1 continued. I've repeated my function of x equation from the previous slide that was given in the question, and I've repeated my function dash x equation from the previous slide, which we calculated from differentiation. We're now going to use Newton-Raphson technique, which is an iterative technique. Usually 3 iterations home us in on an accurate value of the root, providing our initial estimate is reasonable. So for the first iteration here, using the values on the previous slide, we found that a root occurred between x equal to 1 and x equal to 2. The magnitude of the remainder was smaller when x equal to 1 than when x equal to 2. So therefore it would suggest that the root is closer to x equal to 1 than x equal to 2. So for my initial guess here, I'm going to make the assumption that the xi, my first guess, is 1.2. And that is my best guess. You may decide to take 1.3 or 1.1. So using the Newton-Raphson technique, the first thing I need to do is to find my function of x. So here, my function of x, my x is 1.2. So all I do now is put 1.2 wherever I see an x in the above equation. So I get 1.2 cubed upon 3 plus the 1.2 squared upon 2 plus the 1.2 minus the 2. Evaluating, I get 0.496. Next I need to determine the function dash x. This is the first differential. So again, function dash x of 1.2 in this case. I'm now using the above equation for function dash x. So I get 1.2 squared plus 1.2 plus 1. Evaluating, I get 3.64. So now to find the next value of the estimate of the root, the xi plus 1, I need to use my xi and then minus from that the function of x divided by the function dash x. That's the Newton-Raphson formula. So to get the next estimate for the root, if xi plus 1 is going to equal to the 1.2 in this case, the xi, minus the function of x, in this case that's 0.496, divided by the function dash x, in this case that's 3.64. That gives me an estimate of the root for the next iteration of 1.0637. So now I'm on to my second iteration, and this time my xi now is the 1.0637 from the first iteration. Now the process repeats itself totally. I find my function of the xi, so function of the 1.0637, so that's 1.0637 cubed divided by 3 plus the 1.0637 squared divided by 2 plus the 1.0637 minus 2. That gives me a value of 0.0306. So I've got my function of x value determined, and now I need to work out my function dash x value, so function dash of the 1.0637, again just put the 1.0637 for x in the function dash x equation and evaluate, That gives me 3.19516 in this case. So that's my function dash x value. To work out my next estimate for the location of the root, the xi plus 1 value, so that's 1.0637 minus the 0.0306 divided by the 3.19516, and that gives me a next estimate of 1.05412. So example 1 continued. Again, I've repeated my function of x equation, my function dash x equation here for convenience. I've also repeated the second iteration from the previous slide for convenience. We use an xi value of 1.0637, and using the Newton-Raphson technique, the next estimate was 1.05412. So for the third iteration, hopefully you've attempted this, using an xi of 1.05412. We have to work out our function of x value. So in this case, put in the 1.05412 into the equation for the function of x, gives us a value of 0.00001396. Put in the value of 1.05412 in the function dash x equation, and the evaluating gives us a value of 3.16529. And then working out the next estimate for the root, that works out to give us a value of 1.05408. So after 3 iterations using the Newton-Raphson technique, we find a root at the value of 1.054 to 3 decimal places. Example 1 continued. For reference, had we plotted the cubic equation y is equal to x cubed divided by 3 plus x squared divided by 2 plus x minus 2, we would have plotted this shape here, and we would have noticed that a root would have occurred round about 1. So our estimate from a graphical perspective here for the first value of x might have been the value of 1, which would have been quite close to the root. Example 2. We're asked to solve the equation 3t squared minus 10t is equal to 14 to 3 decimal places. This is a quadratic equation, and we know we could solve this using a quadratic formula, but I'm going to use a Newton-Raphson technique here to show again an illustration of the process involved. As this equation is a quadratic in t, there will be 2 roots for us to find. As with all numerical solutions, we first of all need to determine an approximate location for the roots. And we can do this by sketching the curve or by trial and error. I'm going to look at the trial and error process here initially with you. All we do is the trial and error process is determine the function of t and then put values of t into the equation, calculating the remainder. Where we get changes of sign between different values of x, we have a root location. So first of all, let's find the function of t in this case by simply rearranging the equation given in example 2. So rearranging to get all the terms onto one side of the equation, my function of t in this case will be 3t squared minus 10t minus 14. In other words, I add 14 to both sides of the equation given in example 2. So that will equal to 0. So back to my trial and error process. If I start with the value of 6 for t, I simply put 6 into the function of t equation. So that will be 3 times 6 squared minus 10 times 6 minus 14. In this case, the remainder is positive 34. If I put the value of 5 into the function of t equation, that will now be 3 times 5 squared minus 10 times 5 minus 14, producing a value of positive 11. So no change of sign between t is equal to 5 and t is equal to 6. If I now put the value of t is equal to 4 in the equation, so I get 3 times 4 squared minus 10 times 4 minus 14, that gives a remainder of negative 6. So now I do get a change of sign. So between the t is equal to 4 and t is equal to 5 values, this change of sign means a root occurs. Now looking at the magnitudes of the remainder, I've got 11 when t is equal to 5, I've got 6 when t is equal to 4, so this suggests that the root is closer to the t is equal to 4 than t is equal to 5. So my initial estimate I'm going to use from the value of tn in this case is 4.2, because I think the root is closer to t is equal to 4 than t is equal to 5. So now I have my initial estimate of a root of this equation. We know it's around t is equal to 4.2. I can use the Newton-Raphson technique to home in on the root. But first of all, to use the Newton-Raphson technique, I have to find what's called the first differential, the function dash t. So differentiating the function of t equation, is 3t squared minus 10t minus 14. I just repeated the standard derivative table here for convenience for ax to the n. We find that we get 3t squared, the ax to the n differentiates to an x to the n minus 1, or in this case that will be 6t. The negative 10t differentiates to negative 10, and the constant negative 14 disappears when we differentiate. So now we have our function dash t equation. Example 2 continued. I just repeated the function of t equation from the previous slide and the function dash t equation from the previous slide. So applying the Newton-Raphson technique to this problem to find the first root, positive root we think, it starts at the value of tn of 4.2. That's my first iteration. 4.2 is the value from the previous slide we estimated as a root location. The first thing we need to do is find the function of x, or in this case the function of t value. So putting the value of 4.2 into the above equation of function of t, we get a value of negative 3.08. Next, calculating the function dash x term, in other words the function dash t term in our case, putting the value of 4.2 in the function dash t equation above, we get a value of 15.2. Now evaluating the function of t divided by the function dash t, using the values in our table here, that gives a value of negative 0.202632. So now using the Newton-Raphson equation to find the next value of t for our second iteration, we have tn minus the function of t divided by the function dash t. So in this case that will be 4.2 minus the negative 0.202632 value, so that gives a value of 4.402632. Notice I'm using a significant number of decimal places here to make sure I do not truncate my number or induce errors in my calculations at an early stage. Iteration 2 is undertaken in a similar way as iteration 1. The only difference now is we're using the tn value of 4.4026 from our first iteration. I'll encourage you to work through the rest of the slide yourself there to find the various values for iteration 2. What we end up with is a value of 4.395128, which we then take forward to iteration 3 here, using this value for iteration 3. And eventually we find a value of 4.395 for the value of t and the root location. So for our positive root, the value of t we estimate from Newton-Raphson technique is equal to 4.395. That's the 3 decimal places. Example 2 continued, and again I've just repeated the function of t equation from the previous slide and the function dash t equation from the previous slide for convenience. What I would encourage you to do is stop the presentation and now try and find the negative root location. We need to get an initial estimate of the value of t, and we can find that from our trial and error process on the previous slide. So from our trial and error process, if we continue to put the values of t into the equation, we eventually find that when we put negative t into the equation, we have a remainder of negative 1, so a negative remainder. If we put the value of negative 2 for the value of t into the equation, we have a positive remainder, positive 18. So we have a sign change between t is equal to negative 1 and t is equal to negative 2. Looking at the magnitudes of the remainders there, the magnitude for the t is equal to negative 1 is only 1, and the magnitude for the t is equal to negative 2 is 18. So this would suggest that the root is very close to the t is equal to negative 1. So my initial estimate for the value of t would be negative 1.1. That's my best guess. You may use negative 1.2, negative 1.3, but my guess is negative 1.1. So I'd encourage you to stop the presentation here and undertake the Newton-Raphson technique for the first iteration using a tn value of 1.1, and using your 3 iterations find the negative root value for t. Example 2 continued. Here is the full work solution for the negative root, commencing with a tn value of negative 1.1. I'd encourage you to stop the presentation and review this solution in line with your values to see if we agree. The final value of t I've got for the negative root is negative 1.062 to 3 decimal places. If we now look at a graph of the function of t, the 3t squared minus 10t minus 14, which was on a previous slide, we can see that the roots from the graph would be in the region of 4.4ish and in the region of negative 1.1. So from the graphical method, how we sketch the graph to begin with, we may have started off with closer estimates of the values of the roots than perhaps we did with the trial and error method. I just wanted you to see how the trial and error method works, but you can also use the graphical method should you want to. Certainly the roots we have found from the Newton-Raphson technique look quite accurate when viewed on the graphical solution here. I will leave you with some tutorial questions to attempt. You should use the Newton-Raphson technique to solve all of these problems. In question 1, we're asked to find the roots of a quadratic equation. The x squared minus 2x minus 13 is equal to 0, 3 decimal places. Obviously we can solve this equation using the formula, but we need to use the Newton-Raphson technique for this solution. Question 2, we're asked to find the positive root of the cubic equation 3x cubed minus 10x equal to 14. Don't forget to rearrange the equation to get all the terms onto one side to begin the problem and then solve for the positive root. So to provide you with an initial estimate of the root, you could sketch the curve or use the try and error method. You're looking for the positive root there. Question 3 wants you to find a positive and a negative root of a quartic equation x to the 4 minus 3x cubed plus 7x equal to 12. Again, make sure you put all the terms onto one side of the equation before beginning the solution. Question 4, we're asked to find two roots of the quartic equation, shown here, which is already rearranged for us. Now question 5, we're asked to find the root of the equation 3 multiplied by the natural log of x plus 4x is equal to 5, to 3 decimal places. Now up to now, all the differentials have related to the ax to the n format in our standard differential tables. This one now relates to the ln ax format. You have ln 1x effectively here. So when you differentiate that term, make sure you use the standard forms in the table. Question 6, we're asked to solve the equation theta cubed is equal to 5 multiplied by cos of 2 theta. Got to find an angle, correct to 3 significant figures. Note that the question hints at using radians mode, so ensure your calculator is in radians mode when undertaking the calculations. Again, you can rearrange all the terms onto one side of the equation and use a try and error approach, or you could use a sketching method to try and come up with the locations of the roots. Question 7, we're asked to find the root of the equation 300 multiplied by e to the negative 2 theta plus theta divided by 2 is equal to 6. Notice in this equation you'll need the standard form of e to the ax, which differentiates to a e to the ax to help you solve this problem. We're asked to find the answers to 3 significant figures. The hint is to plot a graph and estimate the initial value. As I said before, to try and find the initial estimate of the roots, you can use trial and error method, you can sketch the graph using curve sketching techniques, which we've looked at in other presentations, or you could use Excel to plot the curve and then note where the curve crosses the x-axis to give you your initial indication of the root. So don't forget to rearrange all the terms onto one side of the equation before plotting the graph, and noting where the graph crosses the x-axis will give you the location of the estimated root. Tutorial questions continue. There's more questions here for you to attempt should you want to. Here's the bibliography used to help generate this presentation. Some very good textbooks here I'd encourage you to refer to for further information. I hope this presentation has been of use to you, and thank you for viewing.